Hello and welcome, and today we're going to be doing an example of integration in 2D using change of variables. Okay, so let's talk about a particular one. So let's say we have the integral. We want to calculate this integral over some region, and we're going to say it's x minus y over x plus y. And we want to go dA. And the region in question is going to be a diamond shape. And it's going to be a diamond at 1, 0. That's one of the vertices. And another vertice at 0, 1, right there. And another one at 1, 2. And another one at 2, 1. Like that. Okay, so we could probably integrate this one if we found the right path through this through this diamond region. I'm going to call that D, this region here, and we could probably integrate this if we were really clever, but we don't want to try to be that clever. So we can notice though that there are these two functions, top and bottom, and it looks like if we were able to use those as our transformation, we might be able to find a better route through this. So we want to find some transformation t that goes to a space u and v that will help us integrate this thing. So sorry, this is a region R, not D. Okay, so we want to find some mapping, and it has to be, of course, invertible. It has to be a T inverse. Okay, so if we're looking at this component function, we're saying, okay, well, we have both this weird interval, but we also have this strange top and bottom there to this function. So this is, of course, a rational function, and rational functions show up a lot in signal processing and electrostatics and all sorts of things. So we want to try to figure out how to integrate this region. So I'm going to set u is equal to x plus y, and then v is equal to x minus y. All right. So this is nice. So usually we think of t as a function of u comma v, and that's equal to x comma y. But now we kind of have it backwards here. This is actually going to be, if I want to put that in a vector form, this is actually t inverse, right? So we want to think of that as x comma y is equal to u v. All right, so what form is this in? So if this is t inverse of x comma y, this is actually a matrix transformation, 1, 1, 1, negative 1, times x comma x and y, and that's equal to u and v. Now, not all transformations are linear transformations like this, but this particular example lends itself to a linear transformation. All right, so how do we find the inverse to this? Well, it's pretty straightforward. We can we know that this is a 2 by 2 matrix, so this is t inverse. So t inverse, the inverse of an inverse, of course, is then the function itself. So what we do is we know that has to be we take the determinant, so it's going to be 1 over negative 2, so that's taking the determinant. And then what was the formula for computing this is that you flip the diagonals, you exchange the diagonals, right? So that negative 1 goes to the top position and that positive 1 goes to the bottom position. And you take a negative of the off diagonals. And that creates a, we'll call this 1 half, 1 half, 1 half, negative 1 half. And we might as well just test this real quick to make sure this does actually, so does t times t inverse produce the identity matrix. That would be the indicative of that this is true. So we'll do that. So t is 1 half, 1 half, and negative 1/2 times 1, 1, 1, negative 1. So 1/2 times 1, 1, that makes a 1. 1, 1 times 1 times 1/2 minus 1/2 is 0. And if you say it, look up here, 1, negative 1, that becomes a 0. And 1/2 times 1 minus a minus 1/2 becomes a 1. Okay, so that checks out. So now we have our transformation T UV is equal to 1/2, 1/2, 1/2, negative 1/2 times UV, and that's equal to xy. So now we want to write this in terms of the notation we learned from the last video, which is going to be that g of u comma v and h of u comma v, and that's going to be equal to 1/2 u plus 1/2 v, 1/2 u minus 1/2 v. Okay, so that looks good. So let's now that we have our transformation, let's do the Jacobian. Let's compute that Jacobian. So pardon me, I'll move that back. The Jacobian then is, so we need to find our change of variables formula. So remember that the Jacobian formula was dA is equal to the absolute value of GU HV minus GV HU times DU dV. All right, so that's pretty straightforward. It's going to be GU is going to be 1/2 times HV, which is going to be negative 1/2, minus GV is going to be 1/2 times HU, which is going to be 1/2. So that becomes a negative 1/4 minus a negative 1/4, which becomes a absolute value of negative 1/2, which is just 1/2. Okay, so our Jacobian then is 1/2. Our absolute value of the Jacobian is 1/2. All right, so or the determinant of the Jacobian is 1/2, and you'll notice that this actually is, so the Jacobian then, Jacobian was just the matrix T, 1/2, 1/2, 1/2, negative 1/2, right? And if you take the determinant of that and you take the absolute value of the determinant, you get 1/2 coming out of it. Okay, so when we say the determinant of the Jacobian, that is literally the same thing as right here. Okay, so so now we have the formula, so that becomes just 1/2 times du dv. All right, so what we need to do now is figure out what is the shape that gets mapped over here. So let's calculate what this is. So the best way to do it is to just pick a few points and just see where it goes. All right, so what we do is I'm going to start with this first point. We have this 0, 1, and if I were to plug that into my, here it is. So if I put 0 and 1 in there, I get a the result will be, so I gotta find a little spot here to do this on my thing. So if I put 0, 1 in there, I get out of it 1, right? And negative 1. Is that right? Does that look good? Yeah, that looks good. So this becomes 1, negative 1. So we go out 1 space there, and we go down negative 1 space. That's the UV point. Right, so we think of that as, I'm going to draw a little arrow there. I'm going to keep track of where all my points go. Okay? And then I have, how about T of 1, 0, right? So that's this point right here. Right, and that's going to be 1, 1. All right, so that becomes 1 here, and then 1 there. Okay, looks good. So that's this point right here, like that. And because this is a continuous function, it's a pretty good guess that any line between that is going to be also connected, like that. Then finally, now we have 1, 2. So I'm going to put t of 1, 2 in there, and that's going to give us a 3, and then a -1. So I count out 3 points here, and then a -1 in the v direction, and those are going to be connected. And finally, if you put in t of 2, 1, you get out 3 +1. So up there. There you go. So that's 1, -1. That is 3, -1. And so again, this goes to right there. No, sorry. This goes there, and this goes down there. All right. So I'm going to call this new region S, right? And it's a nice square. We can integrate that pretty easily. So let's now we have this part here. So we can do this change of variables now. So again, I said the determinant of the Jacobian was 1/2, and the region then, this new region S, is going to be the set of u comma v, such that u is between 1 and 3, and v was between -1 and 1. So a nice little box. All right. So what we have then is the integral over our region R of the function x minus y over x plus y dA is now going to be equal to the integral S, and I said that u was equal to x plus y, and then v was equal to x minus y. So that becomes a v over u, okay? And then wherever the dA then is going to be 1/2 du dv. Okay, so now let's write it down in terms of the actual limits of integration. We can do 1 to 3, -1 to 1, v over u times 1/2 du dv. Okay, looks good. So so let's compute this integral, and we see this breaks in because we can factor this into a product of two functions each. This is a univariate function, 1 to 3, and this is the u function, so that becomes a 1 over u du, and another integral from -1 to 1 of v dv. Okay, that's easy enough to compute. So this becomes we need to put a 1/2 out front. So 1/2 natural log of u evaluated at 1 to 3 times v squared over 2 evaluated at -1 to 1. All right, so this one computes really easily. So that becomes 1/2 natural log of 3 times, and then this one you see that it is, we plug the 1 into the squared, and so we can put the 2 outside. We get a 1 minus 1. So we see that the whole integral is 0. All right, so the answer is 0. That's what our answer is. So let's go review this. I said that the Jacobian was 1/2, right? So let's look at our diamond shape again. I'm going to look at our region R. I said it was this region like this. Like that. And that's 1, 0, that's 0, 1, and that's 1, 2, and that's 2, 1. All right, and so we see that the side of this diamond, it's a square, is root 2. So the area inside of it is actually going to be root 2, and this other side here is also root 2. It's square times root 2, and that's going to be 2. All right. Now, if I do my mapping T and go over, and what we had was, we had 1, -1 to 1, 1, all the way over to 3, 1, -1, and 3, 1. All right, so the side here, each side there was another square. The side here was 2, and the side here was 2. So the area here is going to be 2. It's going to be 2 times 2, which is equal to 4. So you see it's double the size. So we've expanded the area of integration from an area of 2 to an area of 4. And because of that, the Jacobian was going to be half. So it's going to take whatever the integral was over this broader region S, and we just have to have it to get the correct proportions here. But by also spinning this area and flipping it and stuff, we're able to compute this more complicated function and transform it into something that was much simpler, that we could actually break into 2 separate integrals and compute. Now the question then is, why was it 0? That's pretty straightforward. If we see here in the denominator, we have an x plus y. So where is x plus y constant? Well, it's going to be constant on any line going right through here. Any line here, the function, this whole function is going to be constant. All right. At least the denominator will be constant. And now, if I put a dotted line through here, we say that anytime x is bigger than y, it's going to be positive on below this dotted line here, and you know it's going to be the exact opposite size, so that any point here, any point here, let's say, the mirror image on the opposite side of the dotted line, it's going to be the negative version of the same positive value here. And because we're integrating over this half here and that half there, and they're both equal, they should be equal and opposite, and that's what results in a 0 value for the integral. Now, if you could have identified that at the very beginning and saw that there was this nice symmetry in the area and stuff, then well, all the power to you. But it's not always clear that we can find those little symmetries to make things simple, so we have to resort to change of variables to straighten things out and figure out how to compute them. So thanks very much.